Good morning, everyone. I'm Zhao from Nankai University in China. I'm honored to present our work here, named Contrast and Memorize, Semantic Neighbor Retrieval-Enhanced Inductive Multimodal Knowledge Graph Completion. First, I'll introduce the multimodal knowledge graphs to you. The multimodal knowledge graph organizes multimodal factual triples. The facts in MKGs are stored as triples, consists of head entity, relation, and tail entity as the unimodal KGs. As for the multimodal information, they usually consist of entity names, descriptions, and entity images, and relation texts, mainly including two modalities, text and images. The MKGs have been widely applied to many knowledge-driven tasks, such as recommender system and multimodal reasoning. Then I'll introduce the task we proposed in this paper, inductive multimodal knowledge graph completion. Recent studies mainly focus on the transductive MKG completion. Given a query of head entity and relation, the transductive KGC model predicts the tail entity, and both the head and the tail entities are seen during training. However, new entities usually emerge through time and propose challenges for the MKG model to generalize to new entities. Thus, in this paper, we propose the inductive setting of MKGC to predict the missing links involving new entities, such as the WALL-E maybe first come out in the cinema, and we need to predict the missing links of WALL-E to its production company, and WALL-E is not seen during training, which requires the generalizable MKGC model without retraining to predict that. The related works are categorized to two lines. First, the multimodal knowledge graph completion and the inductive knowledge graph completion. For the multimodal KGC methods, there are KGE-based methods which use the knowledge graph embedding methods and utilize the entity embedding table to store the entities. And there are the two second kinds of methods which are based on the pre-trained visual language model. They usually use the masked language modeling style entity token to predict the entities. And for both of them, the new entities embeddings are randomly initialized in the entity embedding table or the entity token vocabulary, so they cannot generalize to the new entities. For the inductive knowledge graph completion methods, they usually focus on the unseen entity problem, and they usually exploit the pre-trained language model to utilize the transferable textual embeddings from pre-trained language model. And they neglected that the visual representations can also transfer to the new entities. And for the structural information, they usually aggregate the structural neighbors of the new entity to the existing KGs. However, for the emerging entities, their structural neighbors are usually limited. Now I'll introduce our motivations. First, the visual modality can help with the inductive inference. The visual representations can also transfer for new entities, and the semantics in the visual images can help with the prediction. For example, for the picture on the right, that the Pixar text in the query can relate to the Pixar logo in the target entity, and it helps to predict the query. And secondly, existing works have not aggregated the semantic neighbors explicitly. However, for new entities, their semantic neighbors can also imply the true target. For example, the WALL-E is similar to the other films, the Cars, and to predict the WALL-E's production company, we can find that the production company of Cars is Pixar, that the WALL-E's production company is highly probable to be Pixel 2, which indicates the true answer. However, it is not trivial to accomplish that. There are some challenges. First, the multimodal contradiction. We can see that in the knowledge triples, the head entity and the tail entity usually are not the same entity type. For example, the Wally image is not similar to the Pixar image, and they are highly unlikely to include each other in the image, which contradicts with the textual similarity, which are usually related to each other. Secondly, the semantic neighbors are sampled by the embedding representation similarity, but training their representation to bring all the query and embeddings with the same target is really expensive. In this paper, we propose the contrastive learning, memorization, and the retrieval framework named CMR. First, we propose the unified cross-modal contrastive learning to capture the textual, and the textual-visual correlations in the same representation space. It alleviates the modality contradictions in the visual modality by avoiding the impact of visual-visual correlation. Then we explicitly memorize the knowledge representations in the knowledge store and the entity store. During inference, we propose the semantic neighbor retrieval-enhanced inference to aggregate the semantic neighbors at test time, which benefits from the contrastive learning and also requires less training costs. The proposed contrastive learning increases the similarity of positive query entity pair and making the helpful semantic neighbors close. Then I'll introduce our methodology. We utilize the bi-encoder architecture. The query encoder encodes the textual queries with the prompt with a pre-trained language model. And the entity encoder encodes the multimodal entity with the entity descriptions and its visual prefixes. The entity encoder is equipped with the visual mapping network, which transforms the entity image to certain amounts of visual tokens that can be input to the pre-trained language model. Then we train the two encoders with the unified cross-modal contrastive learning objectives. The purpose is to bring the positive query entity pairs close and to the negative ones further. And we propose two contrastive laws. First one is the fusion contrastive laws, which utilize the similarity of textual query and the multimodal entity embedding after fusion, which provides a global alignment optimization. And we also propose a pre-alignment contrastive loss to align the textual queries and the visual prefix embeddings to constrain the visual mapping network to provide more optimization signals. For training, we use both in-batch negatives and the preceding batch negatives. And we fix the visual encoder and only fine-tune the pre-trained language model inquiry encoder and entity encoder and train the visual mapping networks. In the step of memorization, we memorize the knowledge representations in two stores. The knowledge store utilizes the query embeddings as keys and their target entity label as values, which means we can input the query embedding to the knowledge store and retrieve its target entity labels. And we encode all the queries in the MKGs to accomplish that. For the entity store, they utilize the entity embeddings as keys and their entity labels as values. and both the seen entities and the unseen entities are encoded in the entity store. In the inference time, for each query, we retrieve its k nearest semantic neighbors and utilize their negative distance as the probability. We also compare the query with all the entities in the entity store and use the entity similarity to form the probability. The final prediction is utilize a parameter lambda to interpolate two distributions. Next, I'll introduce our experiments. Here are our settings. We augment the inductive KGC datasets with multimodal information, and here is the inductive datasets statistics. And we also evaluate our methods in the transductive ones. Here are our evaluation setting and the implementation details. Here is the main results. We can observe that CMR outperforms both KGE-based methods, which is the first group, and the PLM-based methods, which is the second group. And we also propose the textual version with the ablation of visual modality of CMR, and it also outperforms the textual methods. We also conducted the ablation study, which validates our effectiveness of our two contributions, the cross-modal contrastive learning and the retrieval-enhanced inference. Here is the case study. For the case on the left, the unseen entity Wally has the higher token similarity with the query, while the irrelevant entity has a lower similarity. It indicates that CMR can capture the inductive cross-modal correlations to find the relative entities. For the case on the right, we study the unseen entities in the semantic neighbor retrieval. When unseen entity is in the query, means we need to find its related entity. The semantic neighbor retrieval will find the similar queries and indicate the true answers. When the unseen entity is as the target, we can see that the semantic neighbors can also provide the help to the inference. It's also worth noting that the structural neighbors can implicitly included in the semantic neighbors and helps with the prediction. Here are our other experiments. We validate our effectiveness in the transductive datasets, and for the parameter analysis, we adjust the number of semantic neighbors and the interpolation parameter to find the best parameter. And for the visualization, we can see that the unseen entities can be clustered close if they belong to the same entity type, even though they are not seen during training. And we also explore the effect of pre-trained encoders, and by replacing the BERT with other pre-trained encoders such as CLIP and Roberta, it can improve the performance. Here is our conclusion. We mainly propose the inductive multimodal knowledge graph completion, and we aim to utilize the visual modality and semantic neighbors to help with the prediction. We propose a framework named CMR, including contrastive learning, memorization, and retrieval-enhanced inference. Our experiments we outperforms 14 baselines, and it validates our effectiveness. In the future, there are some lines to explore that includes efficient semantic neighbor training and pre-trained VLM exploration and retrieval strategy enhancement. Thank you for listening.